computer simulations, which is what you see on the bottom, and that gives us a more intimate understanding of exactly where different stresses and strains are occurring, and hopefully one day they'll be sophisticated enough that we can import somebody's specific geometry and predict how injury might occur on that bone. And then on the right-hand side there is an image of the helmet that we're developing in our lab. So we're also working on injury prevention devices. And this has been the focus of my project in my time at UBC. And so I'll talk a little bit about that later. But to kind of sum things up, within my lab, we tend to focus on hip fracture prevention, understanding spine and spinal cord injury mechanisms, and then we're kind of starting to move into this traumatic brain injury and how traumatic brain injuries occur. So, as I mentioned before, my work is focused on furthering the development of the ProNector helmet, and this is a helmet that was designed to prevent injuries, spinal cord injuries in head-first impacts. So it was started long before I ever got to the lab, and was actually awarded the Best of What's New in Popular Science award, which is kind of neat. But basically, our understanding of spinal cord injuries and cervical spine injuries is that they often occur in head-first impacts. So this could result from going over handlebars in a mountain biking accident. It could result from being checked into the boards headfirst in hockey, leading headfirst into a tackle in football. These are all ways in which cervical spine and spinal cord injuries are produced. And as we understand the injury mechanism, basically when the head contacts the ground or another object, it stops on contact. And this causes the loading vector, or the direction of the applied load, to be aligned with the cervical column. And then, while the head is stopped, the torso continues to move towards the head, and this creates a big compressive load on the cervical spine and causes injury. So the idea behind the ProNector helmet is that it moves the head out of the path of the following torso in order to reduce the loads on the cervical spine. So I'll show you a couple of videos here. The first video shows what happens in a typical injury scenario where the head stops and the torso comes in and compresses the spine. That's what you see there. I can show it to you once more. And so you can see that as the torso moves towards the head, that spine gets compressed. And then what we expect to happen with the ProNector is that the head will be guided out of the path of the torso, and we expect that this will prevent injury. So, the helmet pretty much consists of two shells. There's an inner shell and an outer shell, and they're connected by this internal guide mechanism. You can see that in the black box down there, and then in more close up in the right-hand corner. So, in an impact, the little red deployment pin up there can move through one of these two guideways, and that causes either flexion of the head or extension of the head. And depending on where an impact occurs, then we want to guide the head in a different direction. So impacts to the back of the head, we want to guide the head slightly forward, and impacts to the front of the head, we want to guide it slightly backwards. And so my work has been to kind of continue developing that deployment mechanism. And I have done this in a couple of different ways. I've used both physical and virtual testing and prototyping. So on the left-hand side is, again, our drop tower that we use to simulate head-first impacts. And there's actually a crash test dummy head inside of that helmet, and then it's attached to a surrogate cervical spine, which we developed in our lab. And so when we use these drop towers, there's a load cell way at the top there, and then one underneath the impact platform that lets us measure the loads that happen in these impacts. We can put accelerometers in the head, and that way we can measure accelerations. And I have basically simulated the exact same thing in virtual multi-body modeling software, and that can just speed up the whole prototyping process. It reduces costs and reduces time. So those are just a couple of different avenues that I have used to study these injuries and the helmet. So in this video, it shows a standard helmet being dropped, and it's slowed down so that you can see what's happening more closely. So if you just follow the nose, which you see a little bit, I'm sorry the screen is really dark, but if you follow the nose, then you can see that the head just moves straight down in the impact. And that's with a standard football helmet. And then with the Pronector helmet, again, follow the nose, and you'll see that it moves forward just very slightly in an impact. And we found that this is enough to reduce the loads on the spine by as much as 30%, and that's again measured from those load cells that we have in our drop tower. So that's pretty much what I have for you in terms of background. So anybody have questions?